Next session is going to be on a really important piece of the neuroscience ecosystem, a software package called Nilearn. And we're going to have Elizabeth DuPre, who's going to be presenting. I want to just quickly, first of all, remind you all that you need to turn in your projects by the end of lunch. But when we start the first session, we will close, or sorry, when we start the session after lunch, we will close submissions. So you need to have your file. So basically, to submit your predictions, you need to upload the file as a TSV or CSV file to your group's Slack channel. And then make sure and let me and Ariel know which file, like if you've got multiple files uploaded, which one you're submitting. Just submit one project per group, please. Okay. Any questions about that? Yeah. Can you just put it in, say again? Should we push the TSV file to GitHub? If you push the TSV file to GitHub, that's great. That's a good thing to do, just because it'll kind of preserve it in the GitHub history. But we're going to go get it from your Slack channel, so please upload it there as well. Yeah. Okay, and I just want to let everyone know that our speakers for today are here. So we've got Elizabeth DuPre is here, obviously, because she's about to speak. But Wani Wu is also here, and he's going to be giving the last talk today about biomarkers. Yeah, thank you, Wani. He's right over here. If you want to find them at lunch today, they're around, so they'll be here, and you can talk to them at lunch. And since I think Wani is only here today, I just wanted to let everyone know that this is your opportunity to chat with them. Okay, so we now have Elizabeth DuPre to talk about Nilearn. Elizabeth's been doing work on cognitive neuroscience and machine learning for a while, and has been involved with NeuroHackademy for also a while, probably longer than me, actually.
I was a participant the very first year.
Participant the very first year. So this can be your future. Yeah, we're very pleased to have Elizabeth, so please come on up.
Thank you so much. Thanks so much for the introduction. Thanks so much for having me. Always happy to be at NeuroHackademy. I think this is really just a wonderful space, a wonderful time. I hope you're enjoying it. I only got in last night. I am a little jet lagged, so we're all going to get through this together. But we're going to keep the energy going because it's going to help me and hopefully help you to get really excited about something that I'm really excited about, which is machine learning with neuroimaging data. So I work as a core developer on a software library called Nilearn. I just want to point out that this is not just my library. This has been development for over a decade. There's a team of about 8 of us who work on this as core developers right now. Actually, I think we're a little under 8. Oh, I think someone's just. Yeah. I'll leave that to you.
I think it's done.
Perfect. I trust you with that. So this is very much a team effort. But I've been really lucky to work on Nilearn for like 8 years now. And I'm really happy to share a little bit about it with you today, in particular, how it can make your life easier for doing machine learning with neuroimaging data, and also doing some things that are just really useful with neuroimaging data, like plotting that, visualizing, all kinds of fun stuff. I will say this year, for the first time, I'm going to spend a little bit of time on the end talking about something that is another library that's built on Nilearn and is used specifically to do functional alignment with fMRI data, which is a lot of where my research is now. If you've heard of things like hyperalignment, this is that. It's another kind of machine learning, so we'll talk about that a little bit at the end. All that to say, we have a lot of fun stuff to cover. We have an hour and a half, but there's always time for questions. So if there's anything that's unclear, anything that doesn't make sense, please just raise your hand and I will repeat the question if it's here in the room. Otherwise on Zoom, please either speak up or put it in Slack. And Noah has helpfully agreed to ping me if I don't see the message, so we can make sure questions get answered. All right, let's go. So in this tutorial, we're going to talk about Nilearn. I know that earlier this week, there was a session on introduction to machine learning, introduction to deep learning with PyTorch. If you went to the machine learning one, or if you've worked in the space a little bit, you may say, that's kind of funny. It sort of reminds me of scikit-learn, but with Nye rather than scikit. And that's not actually an accident. The team that originally developed Nilearn is partially shared with the team that developed scikit-learn. So Nilearn really builds on scikit-learn. It's designed to basically wrap around scikit-learn and give you a way to do neuroimaging, access neuroimaging data in modern machine learning workflows. So why would we need this, right? Like you say, okay, well, scikit-learn solves the problem. We don't need anything else. Well, usually when we think about working in machine learning contexts, in particular, this may be familiar if you did a little bit of this earlier this week, or maybe on your projects. Usually when we think about machine learning pipelines, we're thinking about tabular data, something where features are already extracted. We have a spreadsheet, we have a pandas data frame, but neuroimaging data doesn't really fit neatly into this box. In neuroimaging data, we have a lot of spatial dependencies between neighboring points, vertices, or voxels. We also have a lot of temporal dependencies between successive data points. So it's not immediately obvious how we should go from neuroimaging data to something we can put in a machine learning pipeline. And Nilearn was originally really designed to bridge this gap and provide you with a lot of helpful ways to make sure you're bridging it appropriately. So what we're going to do in this tutorial is we're going to walk through a few different kinds of analyses that you can do with Nilearn and how we can get from some data. In this case, although there was a great data showcase just before this, we're going to use some data that's actually shipped with the Nilearn library and then later with the fMRLine library that's already loaded in the hub. Thank you to Noah and Ariel. And so you should just be able to run this directly. I should have said two. So what I have on the screen here, I'm going to flip back and forth between the two. The tutorial content is written as a bunch of notebooks. There's this really handy tool called DuPre book where you can make notebooks into websites. That's what I have here. And I quite like it because later when we get to things like figures, the figures display online and like look quite pretty. But hide floating meeting controls. But all the exact same content is here in the hub in these Python notebooks. So if you go to curriculum, DuPre ML neuroimaging, we're just going to walk through these notebooks is basically what it is. Okay, perfect. So the first thing we're going to do is we're going to get some data because it's always helpful to have data to show things on. And for this, we're going to use a data set that's distributed with Nilearn called Fetch Development fMRI, which is actually from Rebecca Sachs's group. The full data set is over 150 children and adults watching a short Pixar film. We're not going to use the full data set just yet, but just to explain that open data is great. And this was originally from OpenNeuro. Okay, so we've already heard a little bit about NIBabble. I call everything Nye instead of Ni. I apologize, both are right. We've already heard a little bit about Ni/NIBabble. And what we're going to do is we're just going to use that library to load in the file that we just accessed. And so here we can see just from NIBabble that it has a shape. So there are 168 volumes, and each has this 3D structure of 50, 59, 50. And so this is great, but again, not totally clear how we could go from something like this to machine learning. So first, let's just look at it because it's always helpful to look at your data 100% of the time. So what we can do, where did I jump? Here it is. What we can do is in Nilearn, we have something called view image, which gives you just a quick little interactive viewer. So here I can see my API that I just downloaded, and I can just kind of browse around and see what it really looks like in this particular volume. So this seems reasonable. It looks like a brain. So what we're going to do is we're going to actually extract signal from it. And this is where I'm going to flip back over to the book. So this is really the question about how do we go from this volume to something we could do in machine learning pipelines, right? And the way that Nilearn solves this is through something called maskers. There's a whole family which makes slightly different assumptions. But the fundamental idea of maskers is you define some kind of mask. It could either be a brain mask, it could be a region of interest. Nilearn can guess one for you based on the characteristics of your image. If you provided an API, it will try and figure out what is your data versus what is the background where there's no signal. There's some kind of mask. And you take that data that we had, remember we had those 168 volumes, each with a three-dimensional shape. So we take that data, which here are represented as cubes, we apply the mask, and then we basically flatten it. So now we get something where we have a matrix, which is great for machine learning. And you can see that the columns are going to be features and the rows are going to be samples. And this is really, really nice because if we go down a little bit, this is exactly the kind of format that scikit-learn expects. So you don't have to worry about, and this is something people often confuse when going from their data to scikit-learn, putting in the wrong dimensionality, so mixing your features and samples, and then you're like, why doesn't this make sense? Nilearn handles it correctly for you right away. Okay, so I told you that there are maskers, there are many different kinds. So just to kind of emphasize this point and show you some of the flexibility you have here, we can define regions of interest, which are things that we're interested in looking at. And for this, we can use many different things. Nilearn ships a number of atlases and regions of interest for you. One of the ones that we ship is called the Multi-Subject Dictionary Learning, or MSDL Atlas, which is basically dictionary learning, which learns relatively sparse representations, was learned on multiple subjects. And so it defines a shared set of probabilistic regions of interest across the brain. So we grab that from Nilearn. Once again, we can learn about it. We see that it has 39 regions of interest and that they belong to different networks, which are all labeled. And then we can actually plot this probabilistic atlas directly in Nilearn, because again, visualizing your data 100% of the time is a good call. Okay, so in that case, because we're doing probabilistic atlases, we're going to do what's called nifty maps masker, right? So the difference between a probabilistic atlas and a deterministic atlas is basically for every voxel, do I have one value or do I have floats that add up to one? And so if it's a binary 1-0, then it's going to be what's called a deterministic or hard parcellation. There you do nifty labels masker. In this case, because we chose something a little fuzzier and probabilistic, we're going to do nifty maps masker. If you say, I don't have any of that, I just have a brain mask, or I just have this one region of interest mask, then you can do nifty masker, for example. I don't expect all of this to make sense right now. What I would say is that Nilearn over the last decade, oh, right, we reorganized that. Over the last decade, we have developed a really extensive documentation, which you can find not at that link, but at nilearn.github.io. Just get rid of everything else. And so if you go on the examples, you can see that we have lots and lots and lots of examples about how to extract data from brain volumes. And this would be where you can see like, okay, I am looking for something that looks like this. What's the example that most closely matches it? Awesome. Okay. So what do we have so far? We have our regions of interest. We have our data. We know what kind of masker we're going to use. So let's go ahead and use it. So we take our nifty maps masker. We tell it, here are the maps that we're going to use. Here are our probabilistic regions of interest. And then what's cool is you can pass all kinds of interesting things, which we'll come back to in a little bit, that make it so it's reasonable to apply to your data. But at the end, what I want to point out here is we have this little dot fit. And if you've worked on scikit-learn, this may be familiar. If you haven't worked on scikit-learn, this is the major scikit-learn convention, where you have these basically estimators. In this case, the nifty maps masker, we're going to fit the estimator, and then we transform data with that estimator later. So here you may say, okay, that makes some sense, but the fit is empty. I don't understand. What is it being fitted on? In this case, because we're fitting the masker to the provided regions of interest rather than to our data, that can stay empty because we're just fitting it on the maps that we provided it, the most probabilistic ROIs. Okay. Hopefully this makes some sense. So now we've taken the probabilistic ROIs, we put them in the masker, we fit it just on those probabilistic ROIs, but now what's really cool is we can transform, using that same masker, our data set. So we transformed that first one that I showed you earlier was 50, 59, 50, 168. And now if I look at the shape of it, I see that it's 168 by 39, which seems confusing, but is actually exactly what we wanted. Why is that? So here, what we can see is that we have the 168. So that was our fourth dimension. That was the time series. And we said that we wanted that to be the first dimension in our matrix because it's the number of samples. So that looks perfect. How do we go from the other three-dimensional shape to 39? Is because there were 39 regions of interest in our atlas. So now what we've been able to do is collapse that data or pool that data appropriately with our probabilistic ROIs to get signal for each of those 39 regions of interest. Yes. Yeah. No.
Picture of the masks is like weird to me because they're outlines. No, down below, like this passage.
Here, yes.
So it's just they are solid masks, right?
Yes.
Plotting it as outlines.
Yes, great question. Okay, sorry, I'm going to just repeat for Zoom and you correct me if I'm wrong. The question is basically on this image on the screen, which we used plot prob atlas. Why are we we're just showing the boundaries of each of the ROIs? Does that mean that what we're actually extracting from is just those boundaries, or are we extracting from the area within them? And indeed, we are extracting from the area within them. They are solid. The reason it's chosen to plot this way is because otherwise it's really hard to see where each region ends and starts, particularly for some of the other atlases, probabilistic atlases we ship like DeFumo, where you can have over, several hundred probabilistic ROIs. If each of them are filled in, it's really hard to be like, oh, where is this start and where does this end? So we just draw the boundaries. But it's a great question. Yeah. No, of course. Are there any other questions right now? There are no bad questions. There's no need to preface about your question, just ask. Okay, perfect. So we feel pretty good. We have gone from neuroimaging data to a matrix that we could just plug into scikit-learn. So we're done. No, we have just started it. There are all kinds of fun things we can do. So one of the next things that we can do is we can do some neuroimaging specific things. So maybe we say, I'm not really interested in doing machine learning just on these extracted region of interest values over time. Maybe I want to do some kind of feature engineering. Maybe I'm really interested in functional connectivity, right? And so what I can do is I can create a connectome. And Nilearn supports doing this in many different ways. So functional connectivity is going to be the pairwise correlation between ROIs in this particular case. We'll talk about some other cases in a minute, but this is kind of the default, let's say. And so Nilearn tries to make this really easy. So from nilearn.connectome, you can do import connectivity measure, and then you can say what kind of connectivity you're interested in. In this case, we're just going to say correlation. And then we can, again, using the scikit-learn API, we can do a fit transform. So fit on the data and transform the data at the same time, that same ROI time series that we started with. And we can get out a correlation matrix, and then we can just plot it. So we have this plot matrix in Nilearn to make it really easy to plot. And it looks like things are really connected. So that's exciting. But what else is cool, let's say, is that maybe you want to see it on the brain. Maybe, we have little labels here, but maybe those don't give a full sense. Again, visualizing data is always better. So we can look at it on the brain, and we can also see with more or less opacity, what does this functional connectome really look like on the brain? So the thing that I pointed, oh yes, please. This was a movie watching data set. Yes, exactly. And one thing I should say about the data sets in Nilearn is that they're really distributed for the examples. So this data set in particular is taken originally from Emily Sachs's group and was originally hosted on OpenNeuro, but we took it, processed it, downsampled it. So I wouldn't necessarily recommend working on this to do a paper or something like that, because it's designed to be quick to download rather than the most high fidelity data. The high fidelity data lives on OpenNeuro though. Perfect. Okay, so this looks like a lot of connectivity. maybe a suspicious amount of connectivity. And so, as I said, Nilearn is really designed to help you integrate neuroimaging data. And in addition to neuroimaging data have these specific shapes, we also know, as I said, that it has all these dependencies. And so there are other useful operations that are built into the maskers beyond just extracting signal in particular predefined regions that allow us to account for some of these spatial and temporal dependencies in our data that we don't want to be learning our predictive models on. So, for example, there's the whole idea of confounding, which you might be familiar with. This can be things like head motion. This can be all kinds of stuff. But our developmental data set includes several of these signals. So again, this is really great that this data was openly available and had this. And we also generated a few more when we did fMRI prep pre-processing. And so we can access these in this particular data set using the confounds attribute just here. So if we do that, we can see that we have different confounds of interest. We have the translation, XYZ, rotation, XYZ, frame-wise displacement. These are all motion related. And then we have our anatomical comp cores, our CSF, and our white matter. So these may look familiar if you work with fMRI to some extent. If you don't, it's basically just a subset of what you get out of fMRI prep. But what's really nice is that we have pre-selected these. If you do fMRI prep, you'll see a lot more. But we pre-selected these because we wanted to make sure that we had several different kinds of noise sources included and that we could just apply them quickly to the data. If you wanted all of them, you could say reduce confounds equals false. But what's nice is that the masker that we had previously allows us to actually directly pass these confounds. So what we can do is say, okay, when I have that masker that I already defined, I have my data, same data, but I also have the paired confounds for that data set. And when I apply the masker, I'm going to account for all of those confounds. I'm going to basically handle them, regress them out. And there's other transformations the masker can do, which you saw earlier, where we had things like high pass filtering. You can also add in smoothing, various transformations of the signal to actually make sure that some of these noise sources are accounted for. And this is really important, actually, because if we do the same exercise of plotting the connectivity matrix, now we see that it looks quite different than it did before. And if we do it on the brain, we also see that we now have many fewer strongly positive functional connectivity points than we did before, which is good. This looks a bit more like what our priors would suggest. Okay, so this is just a plug to definitely make sure when you're doing a machine learning analysis, the data that you put in are going to be the data that you get out, as in so many things. And so making sure the data that you put in through visualization and also through accounting through noise sources are the highest quality possible means that the data that you get out, the predictions, will be of higher quality. Awesome. Yes.
So this was like a continuous movie watching data set?
Yes, sorry, the question was, this was a continuous movie watching data set. Yeah.
If we have like event-related design and we have specific timestamps, then is there a way to specify those in the connectivity?
Yeah, so the question is, if you want to do connectivity analyses and you have event-related, can you specify specific timestamps? So in general, yes, you can basically window the data set and then calculate connectivity within those windows. In not this notebook, but the next notebook, I'm going to talk about doing general linear models with event-related time series. And in that case, I also talk about actually doing a decoding analysis with those derived betas. So there are lots of ways you can play it, but yes, yeah, you can just subset the time series if you really want to do connectivity. Great question. Awesome. Okay, don't hesitate. All right, I just want to show, this notebook is really designed to show you that when we do machine learning with neuroimaging data, as when we do machine learning in all things, we learned all those really nice, useful things. Now we can take them and apply them and actually do an analysis. And what we find when we do the analysis is, depending on the kind of learner we use, we get different results. So this is nice and shows that I think Wani Wu's talk later will touch on this a lot more. But if we wanted to think about, how do we learn biomarkers or other sorts of things, we should be exploring some of these options. So first, we're just going to redo what we did because it's not carrying across notebooks. So we load the same data set and the same probabilistic atlas. But now what we want to do is, rather than just working with that one subject the whole way through to illustrate, we can actually go through and load multiple subjects. Let's just start with 30 subjects, right? Seems fine. So what we're going to extract for each subject is their functional scan, their confounds, because we know that's really important. And we're also going to extract some phenotypic information, which includes, are you a child or are you an adult? Because this data set had both children and adults, not balanced. Important to note. So we're going to extract all this information, and we're then going to filter them and say, okay, I'm going to make a group of children. In this case, of the 30 participants, I have 24 children, and that means I have 6 adults. Okay. This is roughly proportional, just to say that we didn't, choose a bad sample or anything, roughly proportional to the original participant pool, which had 122 children and 33 adults. So again, not balanced. We'll come back to that. But when we did this, if you're following along, it takes a little bit of time. Not too bad, just a little bit. But the reason it takes a little bit of time is because we're transforming, using our masker, every one of those files individually. And then we're adding them to this list called pooled subjects, or appending them to this list, called pooled subjects. So each entry in that list, all 30 entries, have the same shape that we saw before, 168 volumes by 39 regions of interest. Okay, so first, maybe what we want to see is just, what if we just look at the children? Because again, we expect there to be differences between children and adults. So what if we just look at the children in this data set, and we're using exactly the same thing we did before? We're going to create a connectome using correlation just on those children. So we do the same fit transform that we did before, and we get a bunch of correlation matrices. And so we see that if we stack those, we get an array of shape 24 for our 24 children, 39 by 39 for our connectivity matrices, each being 39 ROIs by 39 ROIs symmetric. Okay. And we can also, Nilearn tries to make it easy for you, access the average correlation across all the fitted subjects using this mean attribute. So this is just going to derive the mean connectivity matrix for all our subjects. We can see it has a shape 3939. Feel good about that. All our child subjects, and then we could either plot the mean, or in this case, I'm just plotting the first 3, just to show you that there's a little bit of variability here. And again, these look a lot more like that second connectome we saw in the last notebook, because we are accounting for confounds. Perfect. So now we plot the mean connectome on the brain rather than having many brains. And you can see for children, it looks something like this. Now, functional connectivity, slightly loaded. There are many different ways to do it. There are many different definitions of what it should mean. Nilearn supports a number of those. So maybe instead of Pearson correlation, you're interested in partial correlation, for example, which is basically you're interested in the link between 2 nodes accounting for the relationship with all the other nodes. And so Nilearn allows you to say, okay, rather than just correlation, I actually want my connectivity measure to reflect partial correlation. And then we repeat exactly the same procedure that we just saw above, wash and repeat. So now we have this new connectivity measure object. We do a fit transform on the children, and we can do exactly the same plots that we saw here for the first 3 children, but now using partial correlation. And we see that these plots are much weaker, because now we're accounting for all those other connections. And so we're weakening those direct relationships, or there's less variance in those direct relationships. Yes. No, it's great. So here it's the multi-subject dictionary learning still. The question was which atlas for the ROIs are we using, and it's the multi-subject dictionary learning. Yes, of course. So if you want to customize what you do, back up here where we did MSDL Atlas is fetch MSDL Atlas. If you go to, well, first, let me finish this. Basically, what you would do is when you pass your Nifty masker, you would change what maps you pass here. And if you want to pass an atlas, there are many different atlases you could pass. I will say that Nilearn does not have all of them. So we do support, if you want to get something from Template Flow, which is a great resource. We have hooks for Template Flow, but we support a wide number of atlases. So here you can see our deterministic atlases, things like AAL, Harvard Oxford, Ulish, Schaefer, Talrak, Yo. And we also have a wide range of probabilistic atlases, DeFumo, MSDL, which we're using here. So lots of options. But in this particular tutorial, we're trying to keep it all to one, just hopefully easier to follow. Great question. Yeah. Yeah, so the question is, if you have your own atlas not in MNI 152 space, can you put it in? So yes, that is possible. I will say that it will be slightly more complicated than you see here, just because you have to make sure your data is in the same space and everything else. So we have some resampling functions. For example, here, this is resampling, but this isn't really going to like normalize to a different space. This is just maybe they're on a slightly different grid. If you have to move data to your atlas space, for example, that's not totally within the scope of what we do. But in general, assuming you have done all of those pieces, then yes, the same workflow should work. Yes. Yep. Yes. So the question is, if you have individual like native space atlases per subject, I assume, or yeah. So if you have native space atlases per subject, can you do the same thing? So yes, same caveat. You would need to make sure that everything is in the same space. That isn't going to be something we handle for you, but assuming everything is in the same space, then you can take the same workflow. You just obviously can't do the fetchers, but it's not such a big loss. You have it locally or on the cloud, and you're grabbing it with a CloudPath. CloudPath. Oh, jet lag. Okay, so perfect. I think we were here. Okay, so partial correlations. So yes, so assuming you have some atlas, partial correlation. We've already done Pearson correlation. Now we did partial correlation. We see that the connectomes look significantly weaker because we're accounting for all those other relationships. So we're reducing the amount of variance that can go into each individual link. So the connectomes look weaker. This is important to see, right? We can also look, again, that mean connectome across children. We see it looks even sparser than our previous one. Finally, let's say you're really interested in functional connectivity and you want to keep going and you say, okay, I wasn't happy with Pearson correlation. I'm not happy with partial correlation. What else can I do? So there's another method that Nilearn supports. In fact, we support a number of methods, but one of the methods we've supported for a long time is called tangent space embedding. And the idea is to use both correlations and partial correlations, to capture reproducible connectivity patterns at the group level. So effectively what's happening is that each individual connectome is modeled as a perturbation of the group connectome. So now you can't really interpret the group connectome anymore. That doesn't really make sense because it's a perturbation off of that. But each individual connectome is considered how dissimilar is it from the group connectome, right? So again, trying to make things relatively easy for you to test this in connectivity measure, you can just change the kind. Again, now it's going to be tangent. And we're going to, again, just fit children because we know there's this difference between children and adults. And so we fit transform children, and now we get a bunch of tangent matrices. So these look similar in structure. They're the same form of that 39 by 39 in the case of multi-subject dictionary learning atlas to all the ones we'd seen before, but they look really quite sparse. And we're not going to show the mean connectome here because, as I said before, since all these matrices are modeled as perturbations from that mean connectome, the mean connectome would just look like zeros, basically. Okay, so this is really cool. I like visualizing things. I feel good about what we've learned, but I promised you machine learning. So let's do some machine learning. So maybe what we want to do is actually use all these connectivity patterns to do a classification. Maybe we want to go back to our question of children or adults. So we can do that really easily with scikit-learn, which Nilearn is designed to integrate really smoothly with. So here we're going to import some things from scikit-learn. We're going to import accuracy score to say how well we did. We're going to import shadow-fold split, which is a form of cross-validation. We'll talk a lot about that next. And then we're going to import a model, in this case, a linear support vector classifier. So we have all these kinds of functional connectivity that you saw just before: correlation, partial correlation, and tangent. We have our different classes, which are the groups, children or adults. We have our cross-validation, and then we just take that same list. Maybe you remember at the beginning. Oh, I went really zoomed in. This pooled subjects list, where we just took the masker transform and we appended all the time series, right, for all our 30 subjects. So we take that same list and we just make it an array. So this is the one that takes a little bit longer if you're running it along in the notebook. I would still encourage you to do it anyway. It's always best to run these things so you can play around with it slightly, because that's really how you learn what works and what doesn't. So we're going to define a dictionary of scores where we're going to store things we want. For each kind of connectivity measure, we're going to say that that key will be a list, and then we're going to split our data based on class membership into a train and a test. We take our connectivity measure using kind as whatever it was. In this case, we're going to say vectorize equals true because we know that our connectivity matrices are symmetric. So we're just going to take the upper triangle, let's say, and vectorize it. And then we're going to build these vectorized connectomes for everyone in the training set, fit the classifier within that training set, and then make predictions with classifier.predict for a hell.test subject. And then we just store the accuracy for that cross-validation fold, because again, we're going to do this multiple times. And then after we've done this for all folds, we can show results. And they look like this. So in this particular case, it looks as though we can successfully predict group membership. Is someone a child or an adult? Using, in particular, the tangent space embedding. And here the red line is the chance accuracy level. Yes? Great question. So the question was, is the classification based on the group of 30 or the full data set? In this case, for the example to run quickly, it's just the 30. But you could rerun it with the full data set.
As a follow-up question, how much time is given by
Great question. So the question is, as a general rule, how much data is really required to get an accurate classification with a functional connectivity measure? I would say that's an active research question. It depends. Maybe Wani will talk about this more. It really depends on many factors. In fact, I'm going to show you something just now about the stability of predictions, which suggests that there's probably not one answer to that question. But great question. I agree with you. I have the same one. What other questions do people have? No? Okay. And you haven't pinged me, so I assume Slack is clear. Perfect. Okay, let's keep going. So we did a machine learning model. We have solved the brain. Everything is done. Not yet. So machine learning models, there's the quote that the easiest person to trick is yourself. So it's really good with all models to be able to go through and say, does this really do what I think it did? What is the performance really telling me? And that's a little bit of what I want to touch on in this notebook. Given time, we're not going to be able to go through all of this in depth, but I do want to point to some really important things here. And then I'm here today, Monday and Tuesday, and always happy to chat about how this maybe relates to your work or your projects. Okay, so everything we've done to date falls really broadly under the umbrella of feature engineering. And we have a few other questions too, right? So when we're working with this data, one thing we want to know is what about the model that we use to train the predictions? Is it stable? What kind of information are we getting for it? And how, when we learn these predictions, how generalizable are they? So I learned it in this case in that subset of 30 participants, but I have a whole data set in this case of approximately 160. Does it generalize to the 160? Does it generalize to a new data set that I collect of children and adults watching movies? I don't know. I have no idea. And so these are questions that we want to start asking. So, there's some caveats, and I think this is a really good opportunity because we're all learning together here. Just to say that, like, when we're doing this, we should be thinking about cross-validation and we should be thinking about these questions. So this is from a paper showing results from a review of 100 studies from 2017 to 2019 using prediction or aiming for prediction in fMRI data sets. And what you see is that at least in this sample, which was almost 10 years ago, terrifyingly, but at least in this sample, the majority of data sets weren't doing any form of cross-validation. And so that makes it really hard to interpret what the results actually tell us. So in general, if nothing else, I hope that we all learn to cross-validate because I think it's really great. But one of the reasons that, we have a hard time doing it is because traditionally our sample sizes have been really small. And so for a lot of folks, it's hard to know how to cross-validate or what to cross-validate over. And that's something that will come up in a few places, and I'm also happy to talk about. So why should we cross-validate? Okay, so one of the things that we can think about is the formalism of it. Let's start with that. So for our N observations, we have some variable Y that we're trying to predict. This is just traditionally convention that whatever you're trying to predict is Y, whatever you're using to predict is X. So we have data X that we're using to make the predictions on Y. For example, in this case, we have our neuroimaging data from 155 participants. That's our X. And what we're trying to predict is the age group, and that's going to be our Y. We want to estimate some function. And machine learning is great because it allows us to have really complex functions that we don't need to understand, in particular if you're doing deep learning. But we want some function that is going to best predict Y, in this case, our age group, from X, our data. So we want to minimize, another way to say this, is that we want to minimize the error between our actual Y and our prediction of Y when we apply the learned function to X. We want to get those as close as possible. This is doable in one data set, but we're not really interested in doing it in just one data set. I am not particularly interested in writing a paper that says, on this subset of this data set, I can predict. And I have no idea about anything else, but I did it here, You could write that paper and depending on some things, it might be interesting, but what we want to do in general when we think about biomarkers and we think about these other things is predict on new unseen data. And so what we would like to actually learn is the expectation of our error. So you can think about this as if we had infinite data that we could learn over, what on average would our error be? For some data Y and X. So for all the neuroimaging data, movie watching children and adults, and all of the labels for whether they were a child or adult. From this formalism, which hopefully wasn't too much, we really note two things that are very important. The first is that we need to test our predictions of the model on held out data that is independent from the data used to train the model. Because otherwise, when we go to assess that error, if we are here and we're taking the error between Y and the test predictions, if I learn some model that best does it in a given data set and I apply it in that same data set it's going to look like I did really well because that's where I learned the model. But if I do it on new data, I'll get a more accurate assessment of how this particular function is actually performing. The other thing that is really useful to know is this idea of the expectation. So rather than just doing it once in terms of independent data, doing it multiple times is really useful because it allows us to ask a related question given some future data, given a new data set, given an extension of this data set, can I train a machine learning model using this same framework? What's the relative error that I would expect? Would I expect to be, off 10% of the time, 5% of the time, 1% of the time? I don't know yet until I actually try and test that by varying the data significantly. So there are many different forms of cross-validation. And this is where I should also point out that I've pointed to Nilearn's documentation, scikit-learn's documentation, also fantastic, love. It's definitely worth spending some time in if you're interested in machine learning in any capacity. They also have a MOOC. What does a MOOC stand for? Online course?
Yeah.
Something online course. Something. It's great. Whatever it is, it's great. But it's a whole course where you can just walk through at your own pace to learn a lot of the machine learning ideas that we're touching on here, but not specifically for neuroimaging. Nilearn is going to help us do specifically for neuroimaging. Okay, so I just want to show you quickly that we can do different cross-validation schemes, even in our data set. So if you remember in the last notebook, what we did was stratified shuffle split. I'm going to blame jet lag for that one, which basically says we're stratifying by groups. So we have children and adults, and then we shuffle who's in our train and who's in our test, retaining those proportion, that stratification. So we know we always have the same proportion of children and adults. That's not the only thing you can do, though. There are many things you can do, as you can see on the scikit-learn documentation. But let's do the same framework. So this is exactly the same code as we saw before, just all consolidated because now you've seen it 3 times, but more is always good. So we fetch the data, we fetch the atlas, we fit the masker. We, in this case, are going to go back to Pearson correlation for our connectivity measure. And then we take all the data, the confounds, and the group membership, child or adult, and we use that to generate some time series, which we add to this pooled subjects list. And we also have a groups list where we just say, is this time series belongs to a child or an adult? Okay. So as I said previously, we use stratified shuffle split, and we can see that on average, we get quite good accuracy in this particular case. Oh, and one thing I should say, because it was asked already, you may notice here I don't pass the number of subjects, so that means I'm returning the full data set. So now I'm working with all 155 subjects. Okay, so I get pretty good accuracy with stratified shuffle split, and I can plot what's called a confusion matrix. So I'm just plotting the last cross-validation fold, which is why the numbers are smaller. But effectively, what you can see in something like this is, I'm trying to remember, I believe it's adult is 0, child is 1. Okay, so here you can see what was the true label and then what was the predicted label. So if someone was actually an adult, did I say that they were an adult? 5 times I did that. Someone was actually an adult, I say that they were a child? 1 time I did that. And for children, the reverse. So 0 times I said a child was an adult. 24 times I said a child was actually a child. So it looks like I did pretty well. And indeed, my accuracy reflects that. But this again was done with a model where we accounted for group membership when we did the model, right? So we did that stratification. What if we don't do that? What if we just say, let's take random splits? That's called k-fold. And so here I'm going to do 5 different splits. Now I see my accuracy significantly drops, right? And what happened is that I just say everyone is a child because the data set is unbalanced. And so the best thing the model can do is say, or the easiest thing the model can do is say that everyone is a child because just because there are more children in the data set, the model's right more often. And you may not know that unless you think to go and check and say, what kind of predictions is the model making? And then thinking about balance in your data set. So this is another thing I would encourage you to check out. Okay, for the sake of time, I'm going to skip ROC, but it's super useful as other ways to think about how to measure how well a model worked. Encourage you to check it out later. Happy to talk about it later. Another thing I do want to point out is that small sample sizes in your cross-validation will give a really wide distribution of errors. So this plot is effectively saying if we estimate a model using cross-validation and we have relatively small numbers of samples in our held out cross-validation testing set, and we repeat that many times, what do the errors look like compared to if we split our data set into really big chunks? So our held out testing set has relatively many samples. And here LOO, sorry, is leave one out. And this is to show it generalizes across fMRI and MEG. Rather than show you the figure paper, although it's a great figure, I want to show you the way we actually do it. So in general, what we have is we have relatively large sampling noise in neuroimaging data. As I told you earlier, we have that spatial dependency, we have temporal dependency, we have noise, we have all kinds of fun things that come with working with real people and real data. And we also, in general, have relatively small sample sizes. We're not, working with like ImageNet, tens of thousands. I mean, sometimes you are if you're in UK Biobank, but most of us are not working with very, very large sample sizes. So to show you the problem that I just want to highlight here, we can take our cross-validation test set and just change its size, right? Super simple. So first, we're going to decrease the size of our test set to 15 participants. We're going to keep stratified shuffle split because we learned that was important. So we do that. And here we see we have stratified shuffle split. It seems like we're doing pretty well still, even with 15 participants. Then, and just to say, all I did was in the scikit-learn method, I passed the test size as 15. That was the only difference. Now I can pass the test size as 5. Still doing pretty well, although you can see that now what's actually happening is my mean accuracy is the same, but the standard deviation on that accuracy is doubled, right? Between 10 to 5. And then what you can do is actually say, okay, if I just compare the distribution of errors on my accuracy, the standard deviation on my accuracy for different sizes of my test set, what do I see? So when I have a relatively large test set, here it's 30 participants, I get a much better estimate of what my accuracy is. And that's really useful to go back to that problem of what we wanted to do. If I get a new data set, or, I want to think about how does this generalize to some other not population, but other collection of people watching movies, this would give me a much better answer than if I have this very wide distribution of accuracies, because then I really don't know how well does this generalize to a new population. I have some sense, but it's such a wide distribution, it's hard to say. So that's just a little plug to think about cross-validation because it's great and important. There are many ways to do it, but I think there's some real things here that we can dig into on applying machine learning models, especially to the kind of data that we work with in neuroimaging. Again, in this particular tutorial, I'm doing mostly fMRI, but this is kind of a generic problem for MEG, EEG, anything you have. All right. For the sake of time, I will also skip this, although it's incredibly important as well. Just don't do it. It's like the DARE program. Okay. Now, what if you are maybe not yet interested in doing connectivity, functional connectivity, but you are interested in activity and you just want to start with a general linear model? So can you do this in Nilearn? The answer is yes, you can. You can do it in many places, but one of the nice things about doing it in Nilearn is you can then go and integrate it with other stuff. So for this particular demonstration, I'm going to use the Haxby dataset. There are many Haxby datasets actually, but this is one of the famous ones from 2001, introducing multivariate pattern analysis. So we also distribute a version of this in Nilearn. So I'm just going to fetch one subject with fetch Haxby. And then I'm also going to fetch the stimuli. And I can read a little bit about this data set, although definitely the paper and the PyMVPA distribution has a lot more information. Okay, so just like the development data set, Haxby data set has a lot of really useful things for us. First, we have a mask, which is going to be the brain mask. Really useful to know. We also have functional data, one Nifty file for each participant. One thing to note is that this data set was originally collected in 2001, and it was originally distributed in PyMVPA in the mid 2005-ish. So it doesn't have confounds. So again, not necessarily something to write a paper about, but something to still look through and understand. Okay, so there are some things, though, even though it doesn't have confounds, that are going to be relevant for doing a general linear model. The first is we have these stimuli because we said fetch stimuli equals true. And we therefore can access the original stimuli that participants saw during the experiments. So what we can do is actually view these just using matplotlib, handy dandy, wonderful library. And we can see that there are these general visual categories that were presented, right? Cats, houses, bottles, controlled, shoes, scissors, faces, slightly scrambled. Okay. The other thing is going to be a session target. And this is a bit particular to this data set in terms of its name, but the idea makes a lot of sense. So it's going to be this thing we load with pandas, which is just a CSV, and it gives us some information, labels, and chunks. So what is happening, because every subject only has one run, is the experiment was not in fact one run, it was in fact 12 runs. And so what we've done is we've collapsed or concatenated all runs into a single Nifty file. And so this CSV is going to tell us how to get back out to our things of interest. So what was individual runs, what volumes belong to each run, and what stimuli were presented for each volumes. So there are the same number of entries or rows, excuse me, in the CSV as there are TRs in our Nifty image. So it's a one-to-one mapping. Okay, perfect. So we can access this. We can say, what are the unique labels? And we see they match onto what we saw earlier when we plotted the stimuli. Feel really good about this. We can also look at the runs. What are the unique runs? Match onto the 12. And using these two pieces of information, we basically can create a model of what happened during the run. Also, we can look at the paper, definitely look at the paper. But basically, we can start thinking about, okay, what was going on in the experiment? So this is not what was going on in the experiment. This is maybe slightly confusing, but this is just the idea of thinking about a run as a time series. So in this particular experiment, we were seeing different images, and that's really what was going on here. Okay, so what are we going to do? We're going to go back a little bit of formalism, but maybe a more familiar one. So the same thing, we have something we want to predict, which is y. We have things which we're using to make the prediction, which are x. And we're going to have some parameter estimates for each of the x's, which are the betas, which we're going to learn with statistical learning in this case. And then we have an error term. So to fit this model, all we need are our y's and our x's. We get our y through the func attribute, which is those Nifty files. And to define our x's, we're going to create what's called design matrices. So this includes not only the fact that we had events of interest, but also their timing and information on other known sources of noise. So in particular, if this data set had things like those motion regressors that we used before in the masker, we would use them here. How can we do that? Nilearn tries to make this easy because it does statistical and machine learning. And so what we can do is we create a data frame that has the onset for each of our conditions, the trial type, so that's going to correspond to the stimuli we saw earlier, and rest, and the duration. So how long did each event last? And we can make something just like this. So we know everything was locked to the TR. So we know the duration. We know what the trial type was. And we know when it occurred. And what's cool is we can actually really easily, using make first level design matrix, convert this into a visual representation of a design matrix, which again, visualizing data in all forms is always a good thing. Okay. So yeah, we don't have head motion and other information here, but if you do include it in your design matrices. So we run a first level model just by importing from nilearn.glm.firstlevel, import first level model. And this has the same kind of form as our masker did. It's the same as the scikit-learn estimator. So we define it, and then we can just fit it on our data, passing the events. And then we can actually go through, and with the GLM, we can compute contrasts, for example. So we have contrasts of interest. And we're going to look at those in the next thing, but I just want to show you that Nilearn is trying to make this easy because we all strongly believe in visualizing what you're doing. And so we have these reporting objects where you can go through and see what that you can download as HTMLs and save. And they tell you what version of Nilearn did you use, what was done, what were the regressors. You can learn about the model details. So what were the parameters of the model? Anything in orange, this follows the scikit-learn parameter convention. So anything in orange is not a default. But you have access to all of this. You have that design matrix I just showed you. You have a correlation matrix between your regressors. So lots and lots of things that are really useful to know about your particular data set. What questions do people have about GLMs? Because now we're going to go do machine learning with GLMs. No? Yeah, great question. So the question was, is this run on whole brain? So yes, in this case, the brain mask is whole brain, but so it's massively univariate, so it does every voxel separately. But you could also provide a mask, for example, if you wanted, and only do it within a specific region of interest. Yes.
What do you smooth inside of you? Smoothing or
Great question. So I assume the question was, what does it mean to be smoothing inside the GLM? And I assume you are referring to this. Is that right? No, that's first level design matrix. You're referring to this. Yes, great question. So effectively, first level model is designed to be super user friendly. So it's effectively wrapping Nifty Masker for you. So in Nifty Masker, you can do smoothing where you extract the signal and you apply like high pass filtering, smoothing, all these things. So what's happening inside the first level model is it's running Nifty Masker for you first, applying those transformations to the signal, and then it's going to allow you to go ahead and pass the events and everything else to actually fit the GLM on that clean signal. Yeah.
Step before the GLM, but it is essentially still a step before.
It is exactly. It is so what it's trying to do, so you don't have to use first level model as an object, right? There's actually a function separately where you could pass the data, but it's often quite nice to work with the objects because then you can maintain these kind of fit transform and it's like one flow. But if you think about it as separate steps, you can pull them out into separate steps and do Nifty Masker first and then the GLM second. Either works. Yes.
Is the smoothing run before or after the mask? Is it run on the whole brain or is it run on the mask?
Is the smoothing run before or after the masking? Or is it run on the whole brain or is it run on the mask? I believe it's run after, but I have to check. Now I'm nervous. I think so. But this is one of the things I will also say, if there's anything I can't answer because of jet lag, which is my excuse for today, one of the great things about Nilearn is it's really written to be readable and inspectable. So fun trick. Have we showed the IPython trick already? Okay. So fun trick from Nilearn. Dot image, import smooth image. Smooth image. So, if you do a question mark in Jupyter Hub or in IPython, you'll get the doc string for a particular function. If you do 2 question marks, you'll get the doc string and the actual code for that function. It's handy if you don't want to go to GitHub. But one of the nice things about Nilearn is that this code is really meant to be readable. So here, let's see what I get. I check an image, I have the affine, I smooth the array. So yes, I'm extracting the data first using get data, and then I'm smoothing on it. But I can go and quickly check that because it's written in Python with the goal of being readable and extensible. Yes.
Nilearn, is it like essentially the same similar things at other packages such as Acme and MSL? Like what's like the output of it? Is it helpful for downstream analysis?
Yeah, so the question is, what exactly is the relationship between Nilearn GLM outputs and other packaged GLM outputs? So we have an issue open to try and document this really well, but they're all doing general linear models, so it's very, very similar. There's some slightly different choices that are made in every package. Like if you do FSL versus AFNI, you don't get exactly the same results because they make slightly different choices. Nilearn also makes slightly different choices, but in the same way that you would say, I did an FSL GLM or I did an AFNI GLM, you could just say I did a Nilearn GLM and it's totally feature complete. You don't have to go and then do something else in FSL, for example. You can do cluster correction and everything here too. Yeah, great question. Yes.
Is there a function where you can add the motion of cluster?
Yes, exactly. So this data set is sort of a bad example for that because it just doesn't have any because it's so old. But if you did have some, what you could do is basically just pass them when you fit the GLM. So you would say, just as we did for connectivity measure, you remember we did fMRI, compounds equals confounds, you could do the same thing here. Great questions. Yes. Yeah, how would you add an interaction to your model? So I don't have that example in this tutorial, but I would say that I believe we have an example with that in here. And if we don't, we can talk about it. But yes, it's possible. It's definitely possible.
Would it take into account temporal autocorrelation?
Yes, it does take into account. Sorry, the question was, I don't remember if I repeated the last question. The first question was, can you add an interaction term to your model? And the answer is yes. There's probably an example for it on the Nilearn documentation. If there's not, we can talk about it and or add one. The second question was, does it take into account temporal autocorrelation? And the answer to that is also yes, it does take into account temporal autocorrelation. Perfect. Okay, so we don't have too much time left, and I have 2 more things I want to talk about. So let's go. But again, questions are good. Don't hesitate. Okay, so we did general linear models. We could go in one direction and just continue on general linear models. I want to say there's a lot more here that we haven't talked about. There's the question of, interactions. There's the question of specific things you're going to fit. There's the question of cluster correction, all kinds of really fun stuff, which is in here, but I don't have time for right now. Instead, what I want to talk about a little bit is how you can use general linear models for decoding, because we're going to circle back. It's all linked. So I've hidden a lot of code in the Jupyter book, but if you're here, you'll see that nothing is hidden and everything is free. And if you're also in the Jupyter book, you can just click show and it shows it for you. Nothing's hidden. So the idea, though, the reason I am hiding them by default is because this maybe looks a little familiar now, right? So This is just some warnings. This is just making sure you get the data in the hub where the data is supposed to be in the hub. But what we're doing is we're fetching Haxby again, same subject. This time I'm not going to retrieve the stimuli because we already saw it and we have an idea of what it looks like. Now I'm going to go ahead and define those same design matrices that I designed before. And I'm going to fit a general, at first level, general linear model with those design matrices. And that all was in just a few lines of code. So now what I have for this particular subject is I have beta maps effectively. So these, if you remember in the formalism, let's just go back to the formalism. Here. Our design matrix is our X. Our neuroimaging data, fMRI, is our Y. And so now, because I fit those in the general linear model, I have a bunch of betas. And I can actually take those betas and I can use them, interpret them, project them to be maps, just like the nifty data is. And what's cool is that when you have these statistical maps, we also have information about, again, same thing, what stimuli were being shown and what particular run these occurred in. And so using all of these, we're going to perform a different support vector classifier. And in this case, we could do it through scikit-learn, just as we did before. If you remember with children versus adults, we did a scikit-learn import. I think we did a support vector machine. But here we're going to use the decoder object in Nilearn, which just as the first level GLM wraps nifty masker to make it a bit easier, similarly, the decoder object is going to wrap some of the scikit-learn functions to really make it hard to go away from good best practice. Not impossible, but it just tries to make it easier for you. So what are we going to do? We're going to import this decoder object. We're going to say we want our estimator to be a support vector classifier. We have our brain mask, which came with the data set in this particular case. We're going to set some things. So we're going to say we're not going to standardize the signal because that was already, when we took the beta maps, we're not going to re-standardize from those statistical maps. We're going to put a screening percentile, which is a kind of feature selection. So we're looking for a percentage of voxels that seem to be really active. And we're going to set our cross-validation because we love our cross-validation. In this case, we're going to do leave one group out because we expect that runs, information from the same run is going to have similar, or statistical maps from the same run are going to be more similar to one another than statistical maps from different runs. So we want to basically make sure that we're not training and testing on statistical maps from the same run. We need to split those out. All right, and what can we do? We can fit our decoder on those maps, passing in, so in this case, this is what the X is the maps, the Y is the condition label, what stimuli was being shown, and the groups for the cross-validation is what run it was part of. And then I can just get a mean prediction accuracy from this using the CV scores values. I can take the mean, I can figure out the chance level, and it's going to say, in this case, if you remember, I'm just going to hop over to the stimuli to show you, cats versus everything else, houses versus everything else. This is the classifier that I'm running. So in this particular case, I can see that my classification accuracy just on these beta maps in this one participant is about 75%, and chance level is just above 12%. So I can really successfully predict in this participant what stimuli was shown just from the statistical maps. And I just want to, because we kind of jump back and forth between a few different things, I just want to point out that in general, when we're working with general linear models and we're thinking about them, you know, as objects where that's the final output, that's what's broadly called statistical learning. And the idea of statistical learning is to identify relationships between variables, like bold activity and experimental condition. So we say this is the relationship between the activity I observe, the bold activity I observe in this fMRI time series, and the experimental condition that the participants were presented with within a data set. While machine learning focuses on relationships that generalize across contexts because of that error that I showed you earlier? What's the error between my prediction and my observed? We don't have too much time, so I think I may unfortunately have to skip this, but this is just a really nice demonstration that when you actually look at these maps, so this is the output of a GLM, this is just the beta, the threshold of betas, and this is the decoder weight maps. You need to be careful about what you identify. So would love to talk about that later. Okay. In the last 10 to 10-ish minutes, well, first, are there any questions? My time pressure is not your time pressure. Okay. So in the last 10-ish minutes, I want to talk about something that is not directly in Nilearn, but builds on Nilearn significantly, and is again developed with about a third of the Nilearn core dev team works on this now. And so the idea is looking at generalization, which we talked about earlier, in a very specific way. So if you've heard of this idea of hyperalignment, this is highly related. So when we're working in a predictive context, as we have been for most of this time in a machine learning context, you may be asking, okay, I would like to make data more comparable. Rather than just assessing how the prediction generalizes, maybe I want to train the data in some way to make the data more comparable. And this effectively was kicked off in fMRI with the introduction of hyperalignment by Haxby Group in 2011. But functional alignment has really evolved beyond this to include a range of methods. So in this particular tutorial, for the sake of time, we're only going to talk about procrustes. For those who are not familiar with procrustes, I actually don't think I have the best illustration, but it's effectively a rotation. So you're finding a rotation matrix, right? There are other methods like optimal transport, which we do a lot with, and the shared response model. But to showcase this, I'm going to use an even different data set. And I just want to plug it because we had such a great data set showcase earlier, is the individual brain charting data set, which includes a large number of contrast maps, like over 100, almost 200 contrast maps now, I think they have, from 12 different subjects. In this case, we're going to use a really small selection of those, but if you need process data, they're great. So what's nice about this is the data set includes contrast derived from 2 independent sessions with different phase encodings. So we have the same contrast derived from a session where we have anterior to posterior phase encoding and a second session where we have posterior anterior phase encoding. So these are independent sessions in the same participants. So we can download images for 6 of these subjects. Again, you could download more, but for now, let's just keep it small. And this is all on the hub if you want to play around with any of these data sets. So we'll have images, which is the list of paths for each of the subjects, a data frame, DF, with metadata about each of the subjects. And mask is going to be a group level brain mask, just as it was in Haxby. Okay, so here is just a different data fetcher. It's a wrapper on the Nilearn data fetcher, so the syntax is very similar. We just fetch these particular subject IDs. And here it's all in the hub already. So that's where it is if you need it. Okay, so when we did regions of interest last time, we really focused on probabilistic regions of interest. Let's change things up just to show that you can do other ones. So here we're going to take the Yo Atlas, which is a deterministic region of interest. So either you're in a particular region of interest or you're not, if you're a voxel. And we're going to find every voxel that is labeled 1, because that means it's in the visual network. We're going to just make sure it's in the same space, or not the same space, on the same grid as our IBC images. And then we're going to take all of those IBC images and use that visual mask or we want to be able to do that. So we fit it. And here, I'm just going to show you what it actually looks like. So if you've used Yo, this looks decently familiar. It's mostly the back of the brain. Great. Okay, so now we have this deterministic region of interest. I use multi-nifty masker rather than just nifty masker. The only difference is that rather than doing that little for loop, you can just pass in a bunch and it does the for loop for you. Same principle though, as we saw before. Okay, so what am I going to do with this particular masker and this particular data set? Well, the idea is for functional alignment that we're going to improve the similarity between the two data sets. Now, I've just spent all this time telling you about how important it is to have train and test, and we're going to keep that importance. It's incredibly important. But our goal is going to be to find, whereas before we just had this general error, now we can be a little bit more specific about what we're trying to find with this machine learning model, right? So we're trying to find some minimal transformation P from a source subject S to a target subject T. And what that means is that the distance between, when I apply P to my source subject, the distance between that transformed source subject and the target subject should be as small as possible. What I can do, because that's a very general question, is I can put more constraints on it. This is just the constraints that Procrustes puts, which means that it's going to be a rotation matrix. You do all kinds of fancy things, but what matters is the general framework. So when I'm trying to do this, I need to define a source and a target subject. And I also, again, really important train and test, need to have train and test in mind. So what I'm going to do is I'm going to define my source subjects train images. And that's going to be everything from sub 01 with this phase encoding direction, AP, and my target subjects train images, same phase encoding direction, different subjects. Now, for the test, make sure it's independent. We're going to take the PA phase encoding direction, but I keep the same source and target subject identities. And so what we're really doing is something like this, right? So we have our source subject S, which in this case is sub 01. Our target subject T, which is sub 02. But they could be whatever you want. In the training data, we're going to train a model that learns that transformation P that makes the sub 01 look as similar to sub 02 data as possible. But because we trained it in the training set, it's going to look great there. So what we need to do is actually see how it looks in the testing data. So then we just take the sub 01 test data, we apply that prediction we already learned to it, and then we get an estimated prediction for our target subject. And we can just compare the error. How similar is our target subject to what we actually predicted they would look like? Same framework as before. So the idea, again, is to keep with scikit-learn style conventions because they're great. And so we have this pairwise alignment estimator. So that first, we transform our data using the masker, the multi-nifty masker that we just saw before, where we passed that visual ROI. And because we have our train images, our test images, we get data, source train data, test target train data. We have our pairwise alignment estimator, and this may look kind of similar to the connectivity measure, but instead of kind, we're saying method, and it's Procrustes in this particular case. But there are multiple different methods that are supported. We're going to fit it on our training data, just like we always do. But here we're passing a source train and a target train because we're just on that first row. Then we're going to transform our source test data. So we take that learned arrow and we just use it to make a prediction. And that prediction, we're just going to call our target prediction data. So in general, this is just, I want to point to this as an idea. In general, you can fit this into larger predictive frameworks like we've already seen, or statistical learning frameworks like we've already seen, like the GLM. But in this case, It's just a really small example to show the idea. So I don't have any fun, cool application. Maybe you have a fun, cool application that we can talk about. So instead, what we're going to do is just see how close the values in our target prediction data set are to the ground truth in our target test data. And we're going to do this via this score voxel-wise, which is basically what is the correlation, the voxel-wise correlation between our prediction and our ground truth. And so what I can do is assess a baseline score, which is if I didn't apply any transformation, if I just took sub-01 test data and sub-02 test data, and I looked at the voxel-wise correlation, how similar are they? But then what I'm interested in is this condition, the aligned score, where I take my sub-02 test data and my predicted test data, and I look at the voxel-wise score. And so if I plot the results with Nilearn, this is just inverse transforming using the masker, and then plot stat map, also very handy. What you can see is on top, this is the baseline score, and you can see that there is correlation. Again, we restricted this to visual cortex, so you're only seeing visual cortex. There is correlation between the two subjects in visual cortex, but it's not, there's certainly individual variability as well. Whereas after the Procrustes transformation, you're seeing a lot more correlation between these two statistical maps, suggesting that we've made them a lot more similar than they were when we started. So the Procrustes transformation is moving in the right direction. Okay, this I definitely won't have time for, but just to plug, if you're interested and you have more than 2 subjects, you may be interested in developing a template, which you can also do really easily in this and pass around to all your different analyses. All right, I think I'm at time. So I think we have time for like a couple questions. Yes. If folks have questions. Yes.
I can ask.
Yeah.
So this the last part, the function template. So this is a template we would create, or it creates for us automatically?
Yeah, great question. So the question is the functional template, is it something you have to worry about creating, or is it something that the library creates for you automatically? So yes, right now it's designed to be something that the library learns for you. So the Spark notes of it, although we have a full example, we definitely don't have time to walk through, is whereas before we did the pairwise alignment, now you can do something called group alignment. And for group alignment, you can say a target, and the target would be template, and it will learn the template for you using variational inference, which is just basically a way to say that we're trying to optimize a function to guess what the template should be, or learn what the template should be.
Quick follow-up. It's similar to like a constraint ICA where they have, I don't know if it's familiar with that.
Yeah.
Logic where when instead of getting our own components out of the data, we have a group of components already built in, so the data kind of like
I see.
reverse learns.
So the question is it similar to a constrained ICA? So no, that's a great question. It is a bit confusing because template is used in the ICA context to mean like the effectively the priors. So here, no, there's not a prior. Usually what, that being said, there are people who are working on priors, but in this particular library, there's not a prior. Here, what you would do is you would initialize a functional template using, there's different ways to do it, but let's say you take the average of your different subjects. And then from that average, you would learn transformations from each subject to the template. You would update the template and you would iterate until you reach convergence. It does it all for you behind the scenes, so you don't have to think about it, but how many subjects does one need? It's a great question. So this is also an active research area, but in general, what we've seen is as soon as you have 3 subjects, you can get a benefit from doing a template over pairwise, because effectively you're leveraging group information that's shared across multiple subjects rather than totally relying on an idiosyncratic feature to one subject. So it's pretty early, pretty early. Yeah, of course. Yes, sorry, yes.
You showed us the forecast. He does.
Yes.
Portioned us interested in them. Can you expand on that?
Yes. Okay, we're at 12, so maybe this is a good note to end on, or, and then we'll go. Okay, I'll be really short then, because I know lunch and projects and all the things, but again, I'll be around for a few days, so very happy to chat about it. The high level thing is that here, this is a statistical map from a GLM. that's been plotted and thresholded. And anyway, here what's happening in the GLM is that every voxel, as we said before with statistical learning, is being tested for its relationship with the experimental thing. So it's massively univariate. Here in the decoder map, we're trying to find across all voxels what combination of voxels best predicts what I want to know, which in this case is the stimulus category. And so what you can see when you compare the two maps is this map looks a lot noisier than that map because they assess different things. And the question you may ask is, okay, how do I know which voxels are really important to the prediction? And that turns out to be really hard to answer, much harder than you would think. It's not as simple as just thresholding the voxels for all kinds of reasons that we definitely don't have time to talk about. But what I would say is that in general, this is really a question of feature importance, as it's known in machine learning, which is basically the idea that you have some prediction and you want to know which predictors helped you get your score. And it becomes quite complicated depending on the kind of predictor you use, depending on the kind of learner you used, everything else. So the one thing I plug here, although I'm happy to chat about all of this in more detail, is that some of the Nilearn developers also have this other library called HiDim Stats, which is for high dimensional statistics. And they have a example about exactly this data set, because they're Nilearn developers, and how to try and do feature importance understanding in this particular data set on support vector machine weights. So it's non-trivial, but definitely cautioning that it's not as simple as, okay, which has the highest value? Unfortunately, there's a few more considerations in there because we're not looking at every voxel individually. We're looking at the whole landscape at once. But great question.
All right, I think this will conclude this talk. So let's thank Elizabeth for this great tutorial.